Hey everybody, welcome to Algo Expert. In this video, we're going to be covering the insertion sort algorithm. This is not the most performant of sorting algorithms, but it is a pretty simple one to understand and an easy one to implement. So let's dive into it. How does it work? Well, you've got a list of integers. In front of me, I've got 8, 5, 2, 9, 5, 6, 3. And the way we're going to sort this list is by basically creating a space at the beginning of the list that is going to be a tentatively sorted list, and then iterate through the rest of the array. And at each number in the rest of the array, we're going to insert that number in the tentatively sorted list. So let's see it in action to really understand what I mean by that. We start with the number 8, okay? And this is our tentatively sorted list. In other words, like 8 in and of, like by itself, 8 is a sorted number. And now we start iterating through the rest, meaning through 5, 2, 9, 5, 6, 3. We start at 5, and we try to insert 5 in our tentatively sorted list of 8. In fact, I can even underline this in green probably. So we start at 5, and we say, well, okay, where does 5 go in this list here with 8? Well, it goes before 8, okay? So let's swap 8 and 5. Here, we're going to erase 8, we're going to erase 5, we're going to put 5 here and 8 here. And so now we've placed 5 in this tentatively sorted list. So we can erase part of this line here and extend it to show that 5 and 8 together themselves are sorted. Now we move on to this 2, and we want to insert 2 in this sorted list here. So first, compare 2 to 8. Is 2 less than 8? Yes, it is. So let's erase 8 and 2, and let's swap them. Put 2 here and 8 here. Now, is 2 less than 5? We compare 5 and 2. Yeah, it is less than 5, so let's swap them again. And we'll put 2 here and 5 here. And now we're done, right? There are no more numbers, so 2 is in its final position. And we can see that 2, 5, 8 are in sorted order amongst themselves. So we can extend this sorted list here to have 2, 5, and 8. Now we go to this 9. Let's insert 9 into 2, 5, and 8. Compare it first to 8. Is 9 less than 8? No, it's not. So 9 is actually in its correct position. We know that 2, 5, and 8 are already sorted, right? So if 9 is greater than 8, which it is, then we just don't have to move 9. So here we can just extend the sorted list again. All right, awesome. Now we move on to 5. Compare 5 to 9. We want to insert 5 in our current sorted list. So compare 5 to 9. 5 is less than 9, so we want to erase 9 and 5 and swap them. 5 here, 9 here. Now compare 5 to 8. Is 5 less than 8? Yes, it is. So we swap them. And now compare 5 to 5. Those two numbers are equal to each other. So 5 is fine here. And we're done. We can now erase this line and extend it. And we've got a sorted list with 2, 5, 5, 8, 9. We're left with two numbers, 6 and 3. We want to start by inserting 3 in this sorted sublist. So compare 6 to 9. 6 is less than 9, so we swap them. Put 6 here, put 9 here. Now compare 6 to 8. 6 is less than 8, so we swap them. 6 and 8. And finally, compare 6 to 5. 6 is greater than 5, so it is in the correct position. So we can extend the sorted sublist. So now we are left with 3. We want to insert 3 in the sublist. So compare 3 to 9. obviously, here we're going to swap them. So we're going to have 3 and 9. Then compare 8 to 3. Again, we're going to swap them because 3 is less than 8. Now compare 3 to 6. We're also going to swap them. So now we can put 3 here and 6 here. You can see how this becomes pretty tedious to do by hand, and this kind of gives it away that this algorithm is not that optimal, since you're doing so many swaps and so many kind of iterations, but it is pretty straightforward. So now you compare 5 to 3. They're not in the correct order, so you swap them. Compare this 5 to 3. They're not in the correct order, so swap them. And lastly, we've got 2 and 3. They are in the correct order, so we're done. And now we have really sorted the entire sublist, or the entire list, and all the numbers are in sorted order. So all this algorithm occurred in place within the input array. All we did was swap a few numbers. So the space complexity is going to be O of 1. It's going to be constant space. The time complexity, however, is not going to be nearly as good. It's going to be O of n squared, where n is the length of our input array. And that's going to be really the worst case performance, or the average case performance, when we have to do a bunch of comparisons and a bunch of swaps. You can imagine that if the array, let's say this array had been given to us in sorted order, and we were to apply insertion sort, that would be kind of the best case scenario, where the time complexity would actually only be O of n, because we'd only be doing n comparisons, right? Because we'd start by checking 3. 3 is greater than 2, so we don't have to do a swap. 5 is greater than 3, so we don't have to do a swap. 5 is greater than or equal to 5, no swap, and so on and so forth. And in that case, the time complexity wouldn't be O of n squared. But in the grand majority of cases, the average performance is O of n squared time, and so is the worst case performance. So that is it for the conceptual overview of insertion sort. Let's actually implement it in code now. All right, so we've got our insertion sort function defined. It takes in an array. And the first thing we're going to do is initialize our for loop. So for I in range from 1 all the way to the length of the array. And inside here, we're going to be doing stuff. So why are we doing a for loop? Why are we starting at index 1? Well, remember, we have this sort of tentatively sorted list of numbers, and we want to keep inserting numbers into that list. And at the beginning, our tentatively sorted list of numbers consists just of the very first number in the array. So we start at index 1 here, and that's what we're doing in this for loop. We're iterating through all the numbers starting at index 1 all the way to the end of the array, and we're saying, let's insert each of these numbers in the sorted list. So how do we insert the numbers? Well, we say, let's have a second index, j, that's going to be equal to I. And we say while j is greater than 0, and array j is less than array j minus 1, then we swap j minus 1, and array. And then we decrement j. So let's explain what's happening here. First of all, swap is going to be a helper function that we'll write in a second. All it's going to do is swap the two numbers at the two given indices. But what we're saying with this while loop is, while our current index j, which is the current number that we're looking at, right? The current number that we're trying to insert, is greater than 0, meaning we haven't reached the very beginning of the array, the very beginning of the tentatively sorted sublist. And while our current number is out of position, while array j, which is our current number, is less than the number located right before it at j minus 1. So while our number that we're trying to insert is out of position, swap it with the previous number. And then decrement j to be, to keep track, to have j kind of track the number that we're trying to insert. Okay, and so here, let's write our swap method. So swap is going to take two indices, and it's just going to say, array I, array j equals to array j, array I. In Python, this is a one-liner. In some languages, you might have to declare a temporary variable. Either way, I like to abstract this swap functionality out into another function. It tends to make the code a bit cleaner. But now, once we're done with this while loop and done with this for loop, we can just return the array. As simple as that. So really, insertion sort works by just, looping through the array once, and then kind of looping backwards through the array and finding, doing a bunch of swaps to position our current number at the correct place in that tentatively sorted sublist, to literally insert that number in that sorted sublist. And that's that. And at the end, we just return the input array. Everything is done in place. So this is going to run in O of n squared time in the majority of cases, and it's going to be O of 1 space. So I hope this was helpful. I hope that now you understand how insertion sort works. It's a cool little algorithm, and I'll see you in the next video.